Welcome back to the Deep Dive, where we plunge into complex topics to unearth those surprising facts and deliver those satisfying aha moments. Today, we're diving into a truly fascinating challenge at the cutting edge of artificial intelligence. How do you get AI to generate really long, high-quality videos without, your computer melting down or costing an absolute fortune?
It's a significant bottleneck, to say the least. I mean, the computational cost of generating long videos has been one of the biggest hurdles. But the research we're unpacking today, from a paper titled Radial Attention for Long Video Generation, offers, well, an incredibly elegant solution. What's truly intriguing is that their breakthrough is rooted in a fundamental observation about how attention scores behave in these models. And it's inspired by principles that sound a lot like physics, actually.
Right. So our mission for this deep dive is to guide you through this research, pretty much as you'd find it structured in an academic journal. But, with all the jargon demystified and the key insights brought right to the surface for out, we'll follow the paper's journey from problem to solution and unpack every major finding. So let's get into it.
Okay, so at its core, the problem radial attention tackles is this immense computational expense of current video diffusion models, especially when you try to generate long videos. Imagine you're trying to create, I don't know, a stunning AI-generated film, maybe 5-minute animation, or even just a 30-second commercial. You hit render, and your computer just, well, screams, then crashes, or it takes days. Why?
Well, it's because the underlying technology, specifically something called self-attention, it just blows up in cost the longer your video gets. It scales quadratically.
Quadratically, like O and N squared, right?
Exactly. Think of it like trying to light up every single corner of a giant room with a separate spotlight for every tiny dust particle. It gets overwhelming fast. It's been the ultimate bottleneck. Okay, so that's the problem. What's the breakthrough?
The key breakthrough here comes from a really elegant observation about how that attention actually behaves. The researchers discovered what they call spatiotemporal energy decay.
Spatiotemporal energy decay. Okay, break that down.
Think of it this way. When AI models process video, they use tokens, essentially small data points or patches from different parts of the video, both in space and over time. This decay is the observation that the attention scores, which determine how much one token cares about another, they naturally decrease as the spatial or temporal distance between any two of these video tokens increases.
So things farther apart in the video, either in time or space, just don't pay as much attention to each other.
Precisely. It's like a signal or a wave losing energy as it travels. Distant parts simply don't have as strong of a connection.
So essentially, they discovered that most of the data points don't actually need to talk to each other across long distances in a video. It's like realizing you don't need a super bright spotlight on every single dust particle to see the room. Just focus where the action is.
Exactly. That's the fundamental aha moment here that completely changes the game for efficiency.
Okay, so how does radial attention use that?
Radial attention cleverly leverages this energy decay to create a new, much more efficient attention mechanism. Instead of that quadratic cost, O(n) squared, its target complexity is O(n) log n.
O(n) log n. That sounds significantly better.
It's a truly massive improvement. What does this translate to in real terms? Well, for standard video lengths, you're looking at up to a 1.9 times speedup.
Almost twice as fast, okay.
But it gets even more impressive.
Yeah.
For videos 4 times longer than typical. We're talking about up to a 3.7 times inference speedup and a staggering 4.4 times reduction in training costs.
Wow, 4.4x less training costs. That's huge.
It is. And the best part, it manages to maintain or even improve video quality. Plus, it enables efficient fine-tuning of existing models for longer videos using a technique called LoRA. We'll get into that.
Okay, so before we dive deeper into radial attention itself, let's set the scene a bit more. Why is video so much harder than image generation?
Right. When you move from static images to video, you introduce this additional temporal dimension, time. This dramatically increases the sheer number of tokens, those individual data points from each frame that need to be processed simultaneously.
More data points, more connections needed.
Exactly. And that's precisely why standard self-attention, which tries to connect every token to every other token, quickly becomes prohibitively expensive. It just doesn't scale well at all.
And people have tried to fix this before, right? What were the limitations there?
Yeah. Previous attempts faced significant limitations. Take Sparse Video Gen, or SVG, for instance. While it offered some speed, its dynamic profiling strategy, how it decided which connections to keep, could actually misclassify attention heads on unseen data. This led to degraded performance, particularly for longer videos.
So it wasn't reliable enough. What about other approaches?
Then there are linear attention alternatives, like SANA. These theoretically achieve ON complexity, which sounds amazing, right? Linear scaling. But they often require substantial architectural modifications to the model itself. You have to really change the core structure. And critically, they typically struggle to recover the original video quality or capture local details with the same fidelity as the standard, expensive, dense attention.
So it sounds like previous attempts were either too slow or they compromised quality or they were just too hard to implement without breaking the model.
Pretty much, they're hitting different walls.
How did radial attention manage to sidestep those issues where others struggled? What was different?
That's where radial attention truly shines. It differentiates itself by using a static attention mask. This mask is directly inspired by that spatiotemporal energy decay we just discussed.
Static, meaning it's fixed, it doesn't change on the fly.
Exactly. Because this mask is static and predetermined based on that decay principle, it leads to both impressive efficiency and robustness. It doesn't rely on that dynamic on-the-fly profiling, which, as we saw with SVG, can be unreliable, especially with new data.
Okay, that makes sense. So where does this fit in the grand scheme of video models?
Well, to understand where radial attention fits, it's helpful to trace the evolution a bit. Initially, researchers adapted 2D UNets, which are standard for image generation. Pretty straightforward adaptation. But more recently, the adoption of diffusion transformers, or DIT, as backbones, has led to the state-of-the-art models we see today, like Sora, Hunyuan Video, and Mochi-1.
Right, the really impressive ones.
Yeah. These models achieve their incredible results by using 3D dense attention to capture complex spatiotemporal dynamics, how things change across both space and time. But as we've noted, this comes at that significant quadratic computational cost.
Now, there are general efficiency tricks, aren't there? Like caching or quantization. Do they help here?
They do apply, yes. Things like time-step distillation, caching, quantization, they help optimize video models. But the thing is, they don't fully address this core attention bottleneck. That quadratic scaling problem remains. Radial attention is specifically designed to tackle that problem head-on.
Got it. And what about other attempts at sparse attention? Not the linear ones, but ones that just reduce connections.
Right. And that's also why other sparse attention methods designed for, say, large language models, things like long LoRA or power attention, they prove suboptimal for video generation.
Why suboptimal?
Because they fundamentally ignore the inherent spatial and temporal structure in video data. Text is sequential, but video has this 2D space plus time. It's different. Even video-specific sparse methods like STA and SVG, they tend to struggle with long videos. They often have a fixed receptive field, meaning they can only see so far back in time, or they rely on that unreliable profiling we mentioned, not robust enough.
This brings us back to radial attention's unique strength then.
Exactly. It uses a static ON log n pattern shared across all heads. It's consistent, it respects the structure of video data, and it scales efficiently. This is what truly differentiates it and allows for efficient, longer video extension, which is crucial for practical applications, like generating more than just a few seconds of video.
Okay, so before we get into the real nitty-gritty of the method, let's just quickly recap the basics. How do these diffusion models actually make a video?
Right. So diffusion models synthesize videos by essentially starting with random noise, like TV static. Then, step by step, they denoise this input within a latent space, which is a kind of highly compressed, abstract representation of the video data. The sheer volume of data, even in this compressed form, is immense.
Oh, immense.
Well, for example, the paper mentions generating just a 5-second 720p video requires approximately 115,000 of those tokens we talked about.
115,000 data points for 5 seconds. Wow.
Yeah. So to capture all the correlations across that many tokens, models traditionally use dense attention. Every token attends to every other token. That's where the ON2 time and memory complexity comes from. It's just connecting everything.
Which is why sparse attention is needed.
Exactly. Sparse attention was introduced as a way to restrict interactions to a subset of token pairs using some kind of mathematically defined sparsity mask, saying only these connections matter.
So the big question then is how to design that mask.
Precisely. Can we design a static attention pattern, one that's fixed, that is efficient, yet still expressive enough to capture all the critical information? Can it match the performance of those dynamic methods? And can it also be effectively used during the initial training of these complex models? That's the key challenge they tackled.
Okay, we've seen the monumental challenge, the computational wall, and how previous attempts sort of chipped away at it but didn't quite break through. So how did these researchers crack the code? What's the secret sauce behind radial attention's impressive efficiency? Let's peel back the layers and see how it actually works, starting with their core observation, that spatiotemporal energy decay.
Right. And they didn't just, guess this decay existed. They provided concrete empirical evidence from large models like Hunyuan video. Their observations, which are visually presented in the paper, you can actually see it in the diagrams, clearly show that attention scores truly diminish with both temporal distance, time, and spatial distance.
It's not just a theory, they measured it.
Exactly. And this wasn't just a hunch. The regression analysis confirmed that this decay closely follows an exponential distribution. They got a remarkably high R2 value of over 0.985.
R squared. That means the exponential curve fits the data almost perfectly, right?
Extremely well, yes. It means their mathematical model, describing an exponential decay, very accurately predicts the observed attention scores. They even presented a precise mathematical formulation in the paper, using parameters like alpha to control temporal decay and beta for spatial decay. It's really, as I said, akin to the physical decay of signals or waves in the real world.
So they observe this natural decay, like gravity for attention, and then they engineer their system to mimic it. It's brilliant. How do they actually build that decay directly into the model structure? How does radial attention convert that energy decay observation into compute density decay?
Exactly. They design what's called a static attention mask. It's predetermined. Imagine your video frames laid out on a grid representing both spatial location and time. For temporal density decay, that's decay over time, they apply an exponential decay rule along the temporal dimension.
Okay, how does that work visually?
The attention map is divided into what they call diagonal bands. Think of stripes running diagonally. That central band, which represents attention between tokens in nearby frames, close in time, retains full computation, full attention there. But crucially, each successive band, moving outward, representing frames further apart in time, has half the compute density of the preceding one.
Ah, so it gets sparser and sparser the further away in time you look.
Exactly. Like a flashlight beam. Super bright on what's right in front of you, but the light gets exponentially dimmer the further away things are. This dimming is meticulously planned, cutting down on unnecessary computations between distant frames.
Okay, that covers time. What about space? Spatial density decay.
Right, so here, attention is concentrated on tokens at similar spatial locations across frames. Makes sense, right? A pixel here likely relates most to the pixel in the same spot in the next frame. The diagonal width of these blocks shrinks as the temporal distance between frames increases. So, for very close frames, it looks broadly across space around that corresponding location. But for frames further apart in time, it narrows its spatial focus more tightly around the exact same spot.
It gets more pinpointed over longer time distances.
Yes, and for very distant frames where that diagonal width might drop below, say, 1 pixel, they smartly reduce the frequency of diagonals instead of trying to narrow it further. It becomes more selective spatially.
Clever. And you mentioned another trick, the attention sink.
Ah, yes, the attention sink. This is a crucial, clever detail. Imagine every single data point, every token throughout the entire video, always keeping a direct line of communication or attending back to the tokens in the very first frame.
Everything looks back at the beginning.
Bye. Think of that first frame as a stable anchor, a consistent reference point that every other part of the video refers back to. This is key for making sure the whole video feels coherent and consistent, not jumpy or disconnected, especially as it gets longer. It maintains global context.
Okay, so this static mask approach sounds much more robust than something like SVG.
It seems to be. Radial attention unifies spatial and temporal attention into this single static mask, overcoming SVG's dynamic classification issues and its struggle with unseen data. Because it's not guessing, it's pre-planned based on the decay principle.
Let's talk numbers again, the complexity. How does this mask design achieve ON log n?
From a computational complexity standpoint, they showed through derivation how this designed the decaying density. The structure achieves that impressive ON log n complexity for long videos, assuming fixed spatial resolution. And to give you that compelling figure again, when generating a 509-frame 720p video, radial attention reduces attention computation by 9x compared to dense attention.
9 times less computation. That's a game changer.
It's a massive leap. And in their error analysis, looking at how much information is lost compared to dense attention, they demonstrated that the approximation error decreases exponentially with larger decay rates. And empirically, radial attention has a significantly lower mean squared error, MSE, than both SVG and STA.
Lower error means it's closer to the original expensive calculation.
Exactly. A lower MSE indicates higher accuracy in preserving the original attention's fidelity, despite being much faster. Plus, it's designed to be hardware-friendly due to its use of 128 by 128 block sparsity, which makes it more practical to implement efficiently on modern GPUs.
Those numbers are truly striking. Okay, so this elegant engineering works great theoretically and reduces errors. What does it mean for actually using these models, for deployment and fine-tuning?
Right, practicality. This is where low-rank adaptation, or LoRa, becomes an ideal partner.
LoRa. We hear that a lot in AI tuning. Why is it good here?
Because radial attention only prunes unimportant token relations without fundamentally modifying the underlying softmax attention mechanism, that core calculation part. The original pre-trained weights remain largely intact. This means only minimal fine-tuning is required to adapt a model trained with dense attention to use radial attention or to fine-tune a radial attention model for longer videos.
So you don't have to retrain the whole giant model from scratch.
Exactly. LoRa minimizes training overhead, making it much more accessible and cheaper. And interestingly, they found it actually improves video quality by refining only the most critical weights in the attention mechanism related to handling these longer sequences.
Okay, theory sounds great. LoRa makes it practical. Let's get to the proof, the experiments. What did they actually find when they tested this?
Right, the results section. This is where we see radial attention in action across different models and scenarios. The researchers rigorously benchmarked their method on 3 large text-to-video models, Mochi-1, Hunyuan Video, and 1.2.114b. Big state-of-the-art models.
And what did they measure? Speed and quality, I assume?
Yep. They used a mix of metrics. For quality, vision reward, basically. How good the video looks to an AI judge trained on human preferences and technical scores like PSNR, SM, and LPIPS. PSNR and SM quantify visual similarity, while LPIPS measures perceptual similarity, how similar it feels to human eyes. And, of course, efficiency. TFLOP's computation, latency, speed, and speed-up factors. They compared radial attention against a whole host of baselines, SVG, STA, power attention PA, long LoRa, Sana, and Riflex, all run on powerful NVIDIA H100 GPUs.
Okay, comprehensive testing. What's the first big takeaway?
First, training-free inference acceleration. This means just swapping in radial attention without any retraining. At default video lengths, like, say, 117 frames for Hunyuan video or 69 for 1.2.114b, radial attention achieves up to a 1.9x speedup, while crucially preserving the video quality of dense attention.
So nearly twice as fast, same quality, just by using the mask.
Pretty much. And it consistently outperforms other sparse methods like STA and power attention on those key similarity metrics, PSNR and SM. Interestingly, power attention, which also claims ON log n complexity, is suboptimal in practice here.
Why is that?
Because it simply ignores spatiotemporal locality. It doesn't have that built-in understanding that nearby pixels and frames are more related, which is critical for video structure. Radial attention's physics-inspired decay model captures that.
Okay, so it works well for standard lengths. What about the main goal, long video?
Yes, this is where it gets really compelling. Long video generation. They found that the original models, without any further tuning, exhibit significant quality degradation when generating videos much longer than they were trained on. The quality just falls apart. In stark contrast, radial attention, especially when combined with that minimal LoRa fine-tuning, achieves quality on par with LoRa fine-tuned dense attention models.
Wait, as good as the super expensive method, even when fine-tuned?
Yes. And in some cases, it even slightly improves the vision reward over the pre-trained model at the default video length. It seems focusing attention helps. And the efficiency gains here are, as we mentioned, truly massive. For videos 4 times longer, like a 509-frame Hunyuan video, it delivers up to 4.4x training cost reduction and up to 3.7x inference speedup.
Those are the kind of numbers that make long-form AI video actually feasible.
Exactly. This isn't a small tweak. It's a monumental shift in feasibility for generating extended video content.
And you mentioned LoRa compatibility earlier. How does that play out?
Right. Another incredibly practical win is its compatibility with existing LoRa's.
Oh.
This is huge because it means radial attention's length extension. LoRa, the small tweak needed for longer videos, is seamlessly compatible with existing style LoRa's. So say you have a LoRa that makes videos in a specific anime style or keeps a character looking consistent. You can use that alongside the radial attention LoRa to generate longer videos in that style.
So you don't have to choose between length and style.
Exactly. You can have both without having to retrain everything from scratch. That's a huge benefit for artists and creators using these tools.
Okay, main results are strong. Did they do any other tests to really nail down why it works so well? Ablation studies?
They did.
Yep.
Let's dig into the details from the ablation study and analyses that truly validate this approach. First, the effectiveness of LoRa. They found that with a radial attention, LoRa fine-tuning matches or even outperforms full fine-tuning of the entire model for length extension.
So the cheap tuning is as good as or better than the expensive tuning?
For this specific task with radial attention, yes, this is a powerful finding. It suggests that radial attention doesn't just make the process computationally scalable, but it also somehow makes the model easier to fine-tune for longer video generation. The structure helps the tuning process.
Interesting. What about the error analysis comparison?
Right, attention error. Remember we said lower error is better. Radial attention achieved a significantly lower MSE of 3.9 by 10 to 3. Compare that to SVG at 4.4 by 10 to 3, and STA way up at 1.5 by 10 to 2. This clearly demonstrates the effectiveness of our mask in preserving attention fidelity. It keeps the attention mechanism incredibly accurate despite the speedup.
And the R-squared value again?
Yes, the regression results. They reiterate that the exponential decay fit for the attention scores has an R2 value over 0.985, solidly validating the theoretical basis for their method. This is really science in action, a core theoretical insight backed up by strong empirical evidence.
Okay, let's try and summarize the core contribution here. Radial attention is an ON log n sparse attention mechanism.
Right, built on that elegant spatiotemporal energy decay principle.
Offering truly massive speedups and remarkable quality preservation for long video generation.
With only minimal, efficient LoRa fine-tuning needed.
Yeah, that seems to capture it.
And if we connect this to the bigger picture, this work really moves us toward scalable, high-quality video generation. It makes a significant dent in one of AI's most stubborn computational problems.
Now, no research is perfect. What are the limitations here? Where does it fall short?
Good point. While groundbreaking, the researchers acknowledge some limitations. Their simplification of the decay model, using just a basic exponential function, might not fully capture all the complex spatiotemporal dependencies in really intricate video data. Future work could perhaps more deeply understand and model the underlying data structure to potentially refine this decay model further.
Makes sense. And what about resolution? We focused on length, but videos also get bigger spatially.
That's a key point. It's important to note that even with these incredible breakthroughs in video length, the method still has quadratic complexity with respect to resolution. Oh, WH2, roughly, where W and H are width and height.
So making a 4K video is still going to be quadratically more expensive than HD, even if it's long.
Yes. While video length, the N in ON log N, is dramatically addressed, generating very high-resolution video still poses a significant computational challenge. That quadratic scaling with resolution remains a hurdle for future research.
Is that resolution barrier fundamental, or could radial attention concepts maybe help there too down the line?
It's a different beast, the resolution challenge, because spatial attention within a single frame is dense. But the paper does open avenues, and it raises an important question for the long term. Can radial attention be used beyond just fine-tuning existing models? The potential for pre-training models natively to support long videos using radial attention from the ground up is left for future exploration.
Training from scratch with this built in.
Exactly. That would be a monumental step forward, potentially making even high-resolution long video generation more feasible eventually, though the core resolution scaling is a separate issue.
Okay. Let's shift gears slightly. Broader impacts. What does this kind of advancement mean for the world? Positives first.
On the positive side, the immediate impact is reduced computational costs. This makes high-quality, long video generation more accessible and practical for a wider range of users, researchers, artists, and organizations.
Democratization? Kind of.
In a way, yes. It's also a clear step towards greener AI by significantly decreasing energy consumption for these incredibly compute-heavy tasks. That's important. And it facilitates wider adoption of generative models, paving the way for really exciting new tools in creative arts, filmmaking, education, you name it. Imagine a small indie game studio being able to generate complex cutscenes, or educators creating dynamic, multi-minute animated explainers with relative ease.
The creative possibilities are huge, but there's always a flip side, right? What are the potential negative impacts we need to consider?
Absolutely. As with all powerful technologies, we must address the crucial negative impacts. The potential for misuse, particularly creating highly realistic deepfakes for fraud or spreading sophisticated misinformation, is significant and frankly quite worrying. Making this tech easier and cheaper could accelerate those problems if we're not careful.
Yeah, that's a serious concern.
There's also the risk of exacerbating the digital divide. Even with cost reductions, the necessary computational resources might still be concentrated, potentially widening the gap between those who have access and those who don't. The researchers, and indeed the broader AI community, emphasize that mitigation requires a multi-pronged approach. Responsible deployment, adherence to strong ethical standards, and the continued development of effective detection methods to identify and counter malicious uses are all critical.
Constant vigilance and proactive measures needed.
Definitely. It's an ongoing challenge.
So, wrapping this all up, what does this really mean for you, our listener? Imagine the possibilities opening up, not just, slightly longer clips, but potentially creating truly engaging films, detailed educational content, complex simulations. It's about pushing the boundaries of what AI can generate while making it more efficient, more sustainable for everyone. This deep dive really shows us how a seemingly simple observation about natural decay, inspired by physics, can unlock incredible advancements in AI. It turns what seemed like an insurmountable computational wall into a much more manageable path forward.
Indeed, and the ongoing quest for efficiency in AI, while maintaining fidelity and quality, is absolutely critical. It's essential for real-world application and, as you said, for democratizing access to these incredibly powerful tools like video generation. It's about making these amazing capabilities practical and widely available responsibly.
And that's our deep dive into radial attention. We hope it's given you a new perspective, perhaps illuminated some of the ingenious ways researchers are tackling the biggest problems in AI, and maybe it's inspired you to dig even deeper yourself. Until next time, keep exploring, keep learning, and keep asking those fascinating questions.